Hello everyone, my name is Shabani from Center for Quantum Phenomena in the Physics Department at New York University. And today I'd like to tell you about the progress we've made in realizing topological superconductivity in planar Josephson junctions. This has been a very collaborative research with researchers at NYU in my group, SUNY Buffalo, Igor Zurek, and John Hang, College of William and Mary, Enrico Rossi, and Wayne State with help from Alex Matus Ibiaga. So, in our quest to realize topological superconductivity, especially if you're thinking about quantum information, we like to follow Majorana zero modes. And while these particles, quasi-particles, have been predicted for a long time now, it was until very recently that we realized actually what are the ingredients and in a toy model, what can we put together to actually create these states. So Kitaev, who basically coined the Kitaev chain model, had basically provided us with a solid state representation of what is needed. And then the theory basically made improvement, and there are requirements in terms of spin orbit coupling, in terms of superconductivity correlation, in terms of magnetic field Zeeman. And there is a recipe now that we have to put together, and there have been lots of review articles on this. Uh, the major goal at the end is that in two dimension or dimension below three, it is possible to get a nanobillion anyons, right? And if we can sort of create and control these quasi-particles with this special statistic, then you can basically do fault-tolerant topological quantum computing. That would be basically quantum computing without error correction. So it's extremely desired and needed for the industry, and if we really want to go forward. Uh, but these things are challenging problems. There have been many proposals of how to realize these Majorana fermions or Majorana zero modes. The very first realistic proposals started around 2010 when Luchin and Orek basically proposed using a nanowires that are approximatized by S-wave superconductivity. These nanowires are one-dimensional, so you actually have to apply a Zeeman field along the nanowire, and they have a spin orbit. There is a modification of this in 2017 that was presented by Pienka and Hell. And these two groups basically propose that instead of having a one-dimensional object, we can make a very long Josephson junction. And then the physics actually kind of maps to the same physics as in nanowires. And then there are more foundational approaches, like basically by STM, we can arrange atoms of a ferromagnet and on top of a superconductor, and then see if there are zero modes at the end of this device. So if we go back to the original Hamiltonian, we basically need a semiconductor with free electrons in it. That, for example, could be indium arsenide because we also need Rashba spin orbit coupling. We need a superconductor that has S-wave correlation, so that could be aluminum, for example. And then you can make a table, right, based on the G factor of the semiconductors or effective mass, basically the properties of the semiconductor and the properties of the superconductor. And for indium arsenide and aluminum, I've listed these parameters taken from this review article. And it turns out the sort of the challenging part is trying to get these states in the presence of magnetic field. So that means that superconducting gap is going to deteriorate. So the higher critical field we have, it's to our advantage. Aluminum critical field in bulk is actually very small. It's a type 1 superconductor. But if you make it very thin, you can actually get really high critical field in the plane, right? And it turns out that's the direction that actually works for this Hamiltonian too, so that would be great, right? So in 2018, And instead of nanowires, we were actually looking at 2DEGs and wafers. And we basically grew these indium arsenide quantum wells near the surface and then managed to put epitaxial aluminum on top of them. And the trick was that to grow aluminum in a 1-1-1 direction compared to the whole other stack that is basically a 1-0 structure. And so once you promote that the structure, you can see the TEM image on the left side, that the interface is quite pristine, and you can see a clear distinction between the quantum well and the superconductor. So we have characterized these materials. Obviously, you want a very good superconductor and a very good semiconductor. And the key is the interface, right? Because to sort of realize that Hamiltonian, all of those terms will really come together at the interface. So we basically have done individual characterization. For example, you can remove the aluminum selectively on top of the quantum well and look at the quantum Hall physics. For example, I'm showing you here Rxx as a function of magnetic field, and you see sort of the oscillations and quantum Hall states in this material. Because the quantum well is near the surface, the mobility is limited to 20-30,000 centimeters squared volt second. The density, you can tune it by doping, and sort of the whole basically band engineering becomes very important, because you also want to get a good overlap with the aluminum. You really don't want your structure to be buried, so there is no interaction with the aluminum. So that checks out as a good 2DEG. For a spin orbit coupling, we have looked at weak anti-localization signal that this indium arsenide quantum wells show near the surface. And indeed, there is a very high density dependent to this Rashba parameter. So if you look at the left axis of this graph, you would see that below 1 e10 to the 12 density, there is really not much of a signal that we can pick up from Rashba parameter. But once you kind of increase the density, it really goes up fast. And if you want to know the energy scale of this spin orbit coupling, it can get up to about 1 or 2 Kelvin. So this is quite substantial for this physics. Now we have to make sure our superconductor basically can stay alive as we apply an in-plane magnetic field. And as I mentioned earlier, we actually do that by making the aluminum very thin, because the field that we need, the direction is in the plane. And Tedro Mesorvi have shown that once you go to ultra thin films, you can actually get to the Pauli limit of the critical field. So here I'm showing you epitaxial aluminum on indium arsenide films with 5 and 10 nanometer thicknesses. And as you see at 0, I guess not 0, but millikelvin temperature, the critical field is quite high, right? At 10 nanometer, you get to above 1.5 Tesla. And at 5 nanometer, you get above 2 Tesla. If we basically assume the indium arsenide band parameters, the field, the crossing happens around half a Tesla. That's where G mu B is almost the superconducting gap. And so both of these values are actually above half a Tesla and quite good for this purpose. So we pursue the Josephson junction route to realize these Majorana fermions. So we start with an aluminum on indium arsenide 2DEG on top left, and with an e-beam writer, we actually pattern the structure such that we want to remove a very tiny strip of aluminum from this pattern, right? So we can do that with a wet etch. This is a transient D etchant that is very well known for aluminum over 3,5 etches. And then we put an aluminum oxide dielectric everywhere and a top gate, so we can actually tune the channel very much like a field effective transistor. So the SCM image, false colored, is shown on the lower right. And you can see sort of that trench in the middle that the arrow says indium arsenide. The junctions are relatively long, so they are 4 micron in width and 100 nanometer separation between the aluminum contacts. So we make a variety of these Josephson junctions. Sometimes there is one T-gate, sometimes there are QPCs at the end. Sometimes we make them mini gates that I will talk more about in this talk. And then we have sort of a variety of this on a chip that an optical image of it is shown on the right-hand side. So then you wire bond your favorite device and then you cool it down. So when we cool down a Josephson junction, obviously usually the quality of the aluminum is really good because we do the aluminum in MBE. It's high purity and there is a lot of control over its growth. The 2DEG, because it's a pseudomorphic growth, this is quite challenging to get really good quality consistently. I mean, it varies and you can obviously pick the best ones. But here I want to show you an example of two samples, sample B and A. And one has a higher mean free pass, the top one, the top left one. Sample B has a mean free pass of 200 nanometer, while sample A has about 100 nanometer mean free pass, right? So if you basically make identical Josephson junctions, so the device geometry is the same, you can see that the supercurrent that sample B shows is about 5 microamp, while the device A, the sample A, shows only about a microamp of supercurrent. So everything is the same, just the quality of the 2DEG is different. And now, I mean, in this paper, we actually go through it in great detail. You can be in short ballistic, you can be in diffusive, you can be in long junction limit, right? And that changes the sort of supercurrent or ICRN values that you get. If you plot ICRN as a function of temperature, for example, for sample A, which had lower quality, you see that the TCs are almost the same, right? Both are around 1.5 Kelvin, but the ICRN at the lowest temperature reaches to about 150 microvolt. While the red one, the red data points, which comes from sample B, they reach up to 500 microvolt. And in a short ballistic limit, you basically theoretically expect a factor of 3 above the gap. So aluminum gap is about 200 to 20. So that times 3 is about 600, 700, right? So the red one is really close to short ballistic theoretical limit even, but while the blue one is not as good. And if you want to basically plot the ICRN as a function of temperature in terms of the transparency, we haven't tried to fit the data, but the dashed line is actually the perfect transparency. And you see the data fits quite well. But so we picked these best junctions, not basically sample B. And we look at this physics that has been predicted from 2017 of how to realize Majorana fermion. So the big idea there was that if you don't bias the junction and you look at the spectrum, the energy as a function of magnetic field, you basically are gapped at the first as you apply the magnetic field in the right direction, which is along the junction. You close the S wave gap and reopen a P wave gap, and basically that new gap, the topological gap, hosts Majorana fermion, which basically shows as a zero energy mode. So if you look at the red graph on the left side, you see that the red basically closes around 0.5 Tesla and basically stays around zero energy. In Josephson junction, we don't measure energy, right? We basically typically measure supercurrent. So if you basically translate this sort of a spectrum to the supercurrent that you expect to see, these calculations are done by Igor Zudik and Alex Matosabbiage. You basically expect the supercurrent also to show some qualitatively similar behavior. The supercurrent basically decreases and then reopens, and that signifies a transition. So, but if you have a junction like this and you can phase bias it at pi, basically if in a no disorder system, presumably the Majorana states at zero energy will start at very, very low field. And that's another way to actually create this. So in this talk, I will mainly stay with the left picture that we do not bias the junction, but we use a squid loop to actually measure the phase of the junction as it transitions from S wave to P wave. So first of all, to just make sure that the induced cap is actually good in our devices, we actually do quick characterization on voltage biased Josephson junctions. And as you see here, we have a relatively hard gap. I mean, in this one, the induced gap is about 160 microvolt. And we can also resolve multiple Andreev reflection. peaks. So 2 delta and 2 delta divided by 2, 2 delta divided by 3. That basically shows that the quality of the interface is quite good. So once we sort of follow the recipe that we have been told by the theorist, we apply a magnetic field along the y direction, which is along the junction, and look at the sort of critical field in the x direction here. So dark blue or black, I guess, in your screen is supercurrent, and you see that basically the supercurrent just diminishes up to 1.2 Tesla very monotonically. So this data is taken at gate voltages that is signified up there as minus 1.5 volt, where the Rashba parameter is very small, as I showed you earlier. This is in the density regime that there is not much Rashba spin orbit coupling. So in the same device, we can repeat this exact experiment by just changing the gate voltage to a higher value where we actually have a substantial spin orbit. So by increasing the gate voltage from minus 1.5 to plus 1.4, now we repeat that experiment, and as you can see, the supercurrent actually closes around 0.6 Tesla and reopens and continues up to 1.2 Tesla, where the critical is the critical field of the junction, basically. So let me actually put this side by side again. So the left side is where we actually have a transition. The right side is where we do not have a transition, right? So one other axis I can show you is that if I park at zero bias and sweep the in-plane field, so the x-axis is the same, but on the y-axis is the same, and the x-axis, now I will actually look at out-of-plane magnetic field. So that would be like the Fraunhofer pattern versus the in-plane field, right? So as you see on the right side where there is no transition, you kind of see these patterns going all the way, and they're so straight up that you can see there is no misalignment in the field. On the left side, you can see that there is actually an abrupt transition when you get to around 0.6 Tesla. And that is also showing up in the bias data. So one thing that I guess we like to differentiate is that if there is sort of this topological physics, the spin orbit should play a big role, and a spin orbit usually breaks the symmetry. So if I tilt the in-plane field away from this ideal By direction, sort of this gap closing should change. And indeed, as we sort of change this theta value from this ideal angle, you can see that on the top left, there is a very clear gap closing and opening. And while as we get to about 20 degrees, sort of that whole transition is completely disappearing. So if we do sort of a phase diagram for the event that I basically just described as a function of gate voltage and in plane field, you see that there are gate voltages that you can go as much as you want in the in-plane field, but you do not see a gap closing. And above some gate voltage, where presumably a spin orbit is strong, you can actually see a transition from what we call S-type and P-type superconductivity. So this is great, but it still is not enough. It would be great if we get more information and more conclusive signature here, right? So we put these devices on a squid loop and we try to measure the phase as we transition from S to P-type state. So for example, here I'm showing you a graph at 850 millitesla. So this is, if you go back, is a field that is strong enough that by just sweeping the gate voltage, I can actually go from S-type to P-type. So by keeping both gate voltages at very low values, I will have a picture that basically have an S junction and S junction in a squid loop. So if I measure the relative phase between the two, it's going to be 0. So that's what the measured phase shift have been showing. So if you look at the graph at the bottom, you see that when I have an S and S, independent of the magnetic field, you basically get almost a vanishing number. When now we can keep one of them at negative value and then fix it, and we know it is S. But then on the other junction, I can sort of slowly increase the gate voltage, and at some point I will cross this the boundary between S and P, and I will enter an S and P configuration. And as you see here on the green symbol and red symbol and purple symbol, it's a quite drastic change. The moment we hit this transition, the phase actually jumps from 0 to pi, and for all these values, and it seems it's kind of converging there. So it's great signature because that's exactly what you expect from Majorana fermions if it's stabilized in a Josephson junction, matches the theory and expectation. And we have now three different, I guess, signature and proof. One is that we see the gap closing and opening, I guess supercurrent closing and opening in our measurement. One is that the field direction is highly dependent, and it only works with the spin orbit direction that is basically described by the theory. And we also measure the phase, and the phase also shows that we can measure the phase while we basically do this transition, and the value is around pi. So this is all great. There was a recent report, a very nice article by Ramon and Leo in Physics Today, I believe, that was basically saying that can we claim that we have seen Majorana, and the answer was we cannot, because the ultimate goal is to show topological protection, right? If we haven't done that, then it is hard to believe all these indirect signatures are actually having something to do with that. So they kind of go and sort of lay out the plan, and sort of the end is that we need to do something that sort of gains information about the statistic of this particle. And as I mentioned earlier, if you have non-abelian statistic, the rules of exchange would be different, right? For example, if you do a fusion rule, you bring two particles and try to merge them together. They would fuse differently than when you bring two electrons together, right? And this non-trivial fusion could actually be a key experiment in this distinguishing whether this physics we are after is something substantial or not. So how can we do that? Very early on, Jason Alicia and Bella Bauer basically came up with this keyboard proposal on nanowires that if we can sort of like tune the gate voltages in a keyboard under the nanowire in the right configuration, you can think of the Majorana wire effectively is changing width, right? So if you go from A to B, you can basically shrink the length of the wire, and by creating the gate voltages on the left side, you can actually make this other segment between gamma 3 and gamma 4. So once you basically can move and you have two pairs, in principle now you can actually merge them together, right? So if you look at our Josephson junction on the right side, so what I've shown so far is the top right, and we have signatures that we have Majorana fermions in that system. So now if I make my single gate into mini gates, in principle, I should be able to actually satisfy the Hamiltonian by increasing the Rashba parameter by going to positive gate voltages, and basically disrupt that Hamiltonian by going to the negative voltages. And then I will have a pair of Majorana. I mean, and then I want to basically fuse them in the middle and then sort of see if I can sort of gain insight into the statistic of this. So again, on the left side, basically there is a Rashba plot that, the green could mean high spin orbit, red means no spin orbit. So basically we can have these P wavelengths and S wavelengths in the middle. So theoretically, you can actually look at some of these and sort of come up with a protocol. And the protocol is that you can create Majoranas. Let's say you go the left path first. You basically create a small Majorana on the left, gamma 1, gamma 2. Then you create another pair on the right side, and then you try to merge them in the middle, right? So if it's a non-trivial fusion, it becomes a probabilistic event. So 50% of the times you can create an electron, 50% it will be nothing. But if it's a trivial fusion, if all the particles we have been following so far is basically they are not Majorana, or they don't have the non-abelian statistic, basically they fuse and they give you identity. And this paper now is actually published in PRL, I believe. Anyway, so experimentally we can actually go ahead and make this junction. So the blue is a Josephson junction. If you stare in the middle, you can even see the junctions is 100 nanometer wide. And these 5 mini gates in the center is trying to basically replicate what I was just describing. And there are 2 QPCs at the end of the junction to actually be used for a readout, but we don't use them, at least in the experiment I want to show you. Excuse me. So schematically, we have a device like this. There is a Josephson junction, aluminum, very same fab. And now the gates are basically now what I call mini gates. And we have 5 of them basically spread out over the junction. If I short all 5 gates and apply negative voltages to them, I get the graph on the right side. So I have some supercurrent, and then the supercurrent basically shrinks and disappears at, I guess in this case, minus 7 volt. I can park them back again at 0 gate voltage and look at the Fraunhofer pattern, right? And sort of this is a nice Fraunhofer pattern. On the y-axis, we have the current bias, and in the x-axis, we have the out-of-plane magnetic field, right? And we see many oscillations, which is nice. The Fraunhofer pattern basically gives us information about the uniformity of the current density in the junction. So if I do an inverse Fourier transform of this signal, I should be able actually to get that current distribution. There is a finite size issue, but if we have many oscillations, we should be able to get a qualitative picture. So if I do that current reconstruction, I can basically drive Jx as a function of x, which is shown on the lower right left. And you see that surprisingly there are 2 peaks at the end of this kind of current distribution, and sort of there is some uniform current in the middle. If you look at the data, you can actually see why this is happening. The first node, while it seems is closing, if you actually stare at the data, there is a gap. And that gap basically suggests that the current is accumulating near the edges of the Josephson junction, not actually uniformly distributed. I mean, you can also think that these mini gates don't have the same area or the same area coverage. So we measured actually the area by depleting 4 mini gates and just activating 1, do a Fraunhofer pattern, and then from the first node estimate the area under that mini gate. Then we do the same thing for the second mini gate, right? Deplete 1, 3, 4, 5, do Fraunhofer pattern for 2, extract the area. So once we did that, I mean, you kind of see that the area does vary a little bit. But what we can do is that we can divide the supercurrent by the area. So basically normalize it. You would expect a larger area would carry more current. But once we sort of divide it, then that basically effect should be canceling out, right? So that's what the lower right graph is showing. IC divided by A as a function of gate voltage. So if I only change the gate voltage of mini gate 1, I basically get the blue curve. So I have some supercurrent divided by the area, and then it depletes, right? It's something that is very surprising is that mini gate 1 and 5, which are the end mini gates, have a much higher IC divided by A compared to the 3 middle ones, which basically are almost identical within the noise of the data. So this is interesting, and I will come back to this, but in an ideal case, all 5 graphs should have collapsed into this one graph, right? If the current was uniform all across the junction. So this very junction could be used actually for realization of these topological states. And one thing that would be really cool to do is to basically change the widths of this kind of effective wire, right? So on the top left, I show current that can basically go through 4 mini gates. The black basically means the current is blockaded. And the right side shows 3 blockaded and 2 allowing the current to pass. And we can do that for all sort of configuration and basically look at the way that the width changes. And we can indeed see a monotonic decrease of the length of the junction, which is very promising once we have a stabilized topological states here. So let me get back to these edge modes. So here is another example of a Fraunhofer pattern that the current is flowing on the right 3 mini gates. And if we do an inverse Fourier transform, you can see that the current reconstruction is showing a peak on the right and sort of a more uniform current redistribution in the middle. This is indium arsenide material, and we know that indium arsenide has a band bending effect near the surface. So we actually did the next nano simulations, and indeed, very near the surface, you actually, the Fermi level basically goes above the conduction band, and you basically get extra carriers near that surface. So once that's happening, it basically allows more current to go through there. And maybe that's indeed the case here. So we thought first maybe we can make a uniform current distribution by lowering the gate, not depleting the end gates, but just lowering the gates just enough that their height is the same as the rest of the middle gates. And that's what is shown on the left side. And you see the peaks on the ends, like -6 volt and -6.1, has brought the peak in the right range, but the connection between these and the middle part is basically missed, right? It goes to 0 and then it comes back up. This is very consistent with this picture at the surface Fermi level band bending, because if you look at this, I guess it's hard, maybe in the zoomed in version, that whole band bending effect at most is like 50 nanometer, right? Our mini gates are about 800 nanometer. So by the time we basically try to balance that sort of edge transport to the right value, we have probably depleted everything else next to it, right? So to get the proper picture here, we can actually deplete the edge mini gates, and then you can see on the right hand side we can recover a very normal looking textbook Fraunhofer pattern with a very nice current reconstruction, which is mostly uniform. So this is for this particular device, the aluminum thickness was too thick, so we didn't have the critical field of about 1.2 Tesla that I showed you earlier. But the new generation of devices have made with very thin aluminum, so hopefully we will have some of these devices in magnetic field and explore the new ideas around fusion and readout. So just want to say that Josephson junctions are very sensitive platform, and that's good. For example, when we wanted to measure the phase, we could use the squid geometry to actually do this. There's a lot of technology that have been already developed on Josephson junctions, so that allows flexibility in the fabrication. And not only they can be phase measured, they can also be phase biased, as I mentioned, and that basically reduces the need for the Zeeman effect, right? So we don't need to have 1.2 Tesla critical field, and maybe we can get by much smaller magnetic field. And there are lots of other considerations that I'm happy to discuss during the conference, but I just want to also highlight the fact that you can even think about this epitaxial supersemi material in the context of quantum Hall state. For example, we have done a recent work that we put niobium tinitride next to an indium arsenide that is in the quantum Hall effect, and you can actually see a substantial cross and rave reflection between the quantum Hall and the superconductor. Yeah, I want to thank you for your attention, and I hope everyone will have a very good interaction during this conference. Bye.